Putting it in the middle warranty the lowest max error. Okay? But I cannot make any other statement. Okay? It turns out that in a few minutes we're going to find out all the behavior of the quantizer, and we'll be able to prove certain interesting properties, right? It turns out that the reconstruction actually depends on the behavior of the PDF. If it's uniform, then we put it in the middle. But if it's heavily biased one side, then we shift our reconstruction that way, because it's a sensible thing to do. It's reasonable, okay? And we can prove that mathematically, showing that to minimize the mean square error of the reconstruction between x hat and x, okay? If we know the PDF of x, we will be able to put the reconstruction at the centroid, okay, of the PDF region. So that we're gonna attack that problem in a few minutes. But right now, let's just say we put it in the middle and see how the behavior of the quantizer, okay? So if I put it in the middle, the typical reconstruction would be this, right? X hat of I is, and this is exactly the middle of xi and xi minus 1, okay? So that's how I get all of those red dots. I just put it in the middle. So this is if you put Q, you follow by Q inverse, okay, by the way, which is a tremendous abuse of notation, right? There's nothing inverse about that, okay? What that means is, for any given interval, you map it to some guy in the interval, okay? And this is called the error of the quantizer, okay? Okay, the difference between x and x hat is the error. Okay, so quantization error is x hat minus x. Okay, what is the maximum quantization error? Can somebody tell me the maximum quantization error in this case? Delta over 2. Delta over 2. Right? I cannot make more error than that. Maximum delta over 2. Warranted. Okay? So as you can see, delta is very important. If delta is small, you make a small error. Delta is large, you make a huge error. Very intuitive, right? So next, there are several types of quantizer. So this is a quantizer we call mid-rise. Mid-rise means it rises up right at 0. Okay? There are many ways that you can partition the intervals, right? So this is one way of partitioning the intervals. This is another way of partitioning the intervals, okay? Where this guy, one of the reconstruction points is exactly at 0. Okay? It turns out that this is very popular in compression, and this is very popular in analog to digital conversions. Okay? In compression, 0 is very important to us. We see from the entropy coding design example that the more 0 we have, the happier we will be. Okay? So that's why we're going to concentrate around 0. We try to generate as many 0 as possible. Okay? That's one of the goals. So let me bypass this and let's start with some quantization error analysis. So the assumption is this, okay? I have an x coming in, just scalar, okay? One single guy, okay? It's a random variable with certain PDF, okay? Maybe Gaussian distributed, Laplacian distributed, or uniform distributed, okay? That is one single random variable coming in. It will come in the Q, it becomes y right here, and then coming through the Q inverse, give me the x hat, okay? The error is defined as x hat minus x. That's what we are. That's the amount of information that we actually throw away, right? So Q, okay. A reasonable thing, okay. This is called a high bit rate assumption, meaning that you're not trying to make delta too large, okay? If you're not trying to make delta too large, Q will turn out to be another random variable, usually 0 mean, and independent of x. Okay, these are the type of assumption that we need to make in order to carry out the analysis. Otherwise, it will be too complicated to work out anything interesting. Okay? So turns out that y will be a random variable too, x hat will be another random variable, q is also another random variable, and I can model it this way. Okay? So I can model it, okay? These two blocks, I imagine like adding noise to my original signal. Right? Agree? Because q is equal to x hat minus x. Right? Q is x hat minus x. So x hat is x plus q. Right? And that's how I come up with this very simple model. So you can treat quantizer at high rate, just like you are randomly adding noise to the original signals. Okay? And that's why we're playing with some of the MATLAB exercise yesterday, right? That's exactly what it means. The quantization noise will be like that. But we add the noise directly to the image pixels. In real life, it doesn't happen like that. Right? We have a transform, like the weighted transform, the discrete cosine transform or something. Right? We never add noise, we never quantize anything directly. Right? So this is the model, and let me write the mean square distortion measure is the expectation of x hat minus x squared, okay, which is just the expectation of q squared, okay, and this is a function of x, right? This is a quantization. So expectation of q squared is nothing more. If you assume that q is zero mean, then it's just the quantization error variance, right? This is just the variance of the noise. Okay. So now let's do this simple analysis. Okay. D of x hat minus x is the expectation of x minus x squared, and I can write it like this, right? Because that's the definition of expectation. Okay. So, and then, now you have multiple quantization levels, right? You have multiple quantization levels. So you can break this large integral into smaller one. So for each of the jumps, right? Okay, each of this integral is for one jump followed by the others, right? And these are quantization boundary. This is the reconstruction within the interval. Okay, so on and so forth. Okay. Now, so I can write this as a summation, right? So I can write this as a summation over L is the total number of quantization intervals that you have. Okay, and I go from 1 to L, and I just do the summation of all the guys, and I have my D. Okay, so this is the mean square error, quantization mean square error that we would like to minimize. Correct? Okay, so let's try to play. Okay, to demonstrate this, let's play with this very simple example. Okay, this is a bounded input, so my x can never go past negative x max and positive x max. Okay, and I have, in this case, I draw 4 quantization intervals, but it can be more, it can be L, okay? So the center reconstruction give me x hat of I being the middle of these guys, okay? And the, how do I get this? Okay, so I'm plotting Q with respect to X, okay? So let's take a little time to try to understand this, okay? Are you okay with this? What is Q? Q is x hat minus x. Q is x hat minus x. Okay? So, Q is x hat minus x. Or am I drawing this right? So x minus x hat. X hat minus x, right? That's true. Okay, so if I happen to be, okay, if x hat match with x perfectly, then I have 0 error, right here, okay? If I happen to be right here and I got mapped to the red dot, this is how much error I make. If I'm right here and I get mapped to the red dot, this is how much error I make. And the upper bound here is delta over 2. The lower bound here is negative delta over 2. Correct? So this is, I figured this out from just x hat minus x. Okay? Now, so are we ready to do some manipulation? What is the error in this case? So first of all, the error bound is q equal to is bounded between negative delta over 2 and delta over 2. That's obvious. Okay? And then at the high bit rate assumption means that instead of working with the distribution of x, I'm going to try to map it into the distribution of q, okay, and work with this plot instead. Okay, so my assumption is this: at high bit rate, there's no correlation between q and x. Okay, and everything will be uniformly distributed. Okay, the quantization error will be uniformly distributed. That means q will live somewhere between here and here, and it will be uniform, so the PDF of q look like this. Okay? Now, if I make that assumption, so the high bit rate assumption is there, and then let's try to do this real quick. Okay? I don't think it's in the is that in our booklet? Is the answer in our booklet? The slides in the in the text, does it have? Okay, so we're going to do the x hat of okay, the distortion, mean square distortion is expectation of q squared. Okay, let's compute this quickly for me. Just a couple lines of math, right? So let's see. Oh, I put the question mark there, right? I put the question mark there. So, the integral of q squared, and then fq of q is just 1 over delta, right? The integration of integral of q squared is 1/3, q to the 3rd power, right? And then what? Instead of negative infinity, positive infinity, you do negative delta over 2 to